Okay, so today we are going to try to use all the relevant dimensions in a problem to allow us to develop models to solve problems, right? And it sounds like magic, and it kind of is. It's even more magic than I think we realize. The more I teach this class, the more I realize that we underappreciate the importance of units, right? So we're taught early on that all equations must be homogeneous in units, and we're all like, "Oh yeah, that makes total sense, right?" Everything should have units of length in Bernoulli's equation, for example. If we're going to have it, if we're going to divide everything by rho and g. But that was not always the case. So if you look back to Hooke's law, for example, if you look back to Hooke's law, it's one thing we're taught about all the time in solid mechanics, for example, and not solid mechanics, sorry, physics. And what Hooke's law says is that the force is equal to the some spring constant times the distance that a spring is stretched, right? And what's incredible about this equation is that that's not how Hooke presented his law. So back in 1678 or so is when he published this law. He didn't state it this way. He stated it as a sentence because back then people didn't have homogeneous units in their equations, so equations weren't that useful to other people. You could develop an equation, and that equation would only work if people measured things exactly how you measured them in that situation, right? So you can imagine that Hooke measured force in some weird kind of version of pounds that was only true in the region of England that he lived in. I believe he was English. I can't remember. And then he just said it was proportional to the length, and he measured that in some weird version of feet because all this stuff varied as you went across the country, right? And you had to solve for each situation what that proportionality constant was on your own. And so he gave his law as a sentence, and everybody was like, wow, you're an amazing scientist. And now we wouldn't even recognize that as a basic finding because we expect these equations that are so darn useful. And the reason they're so darn useful is everyone can use them because everyone has adopted this idea of homogeneous units and common units that make consistent sense, right? And like I said, this wasn't always the case. It took a long, long time for us to kind of rally around this idea of homogeneous units. But even then, it was not until 1914 that we got what I would call our most powerful tool for units, and really that units kind of came into their own. And 1914 is relatively recent. Yeah, it's more than 100 years ago. But at this point in 1914, Einstein was in the thick of developing his special theory of relativity. Okay, so general theory of relativity. He already put out his special theory of relativity, and 10 years before this, the study of quantum mechanics really got a kick in the butt when Einstein published his theory of photoelectric effect, right? And so this idea of quantas of energy was like, oh, wow, this is real. And people started exploring the possibilities of this. So we're right in the thick of people really, really kind of both exploring, well, relatively modern scientific principles, this general theory of relativity and quantum mechanics, and what I would call a third really modern scientific principle, which is that of unit analysis, right? And yet one of these things we take for granted every day, and the other two we're like, well, these are the greatest things ever. And I'd say one of these has had a far greater effect on your life than any other one, and that's units. So, 1914, who and what? Who and what are we so impressed with? Well, it's the Buckingham Pi Theorem. Buckingham, for the guy who came up with it, who published the paper on this, and pi for reasons that we'll see. So what does it say? It says that if we have a physically meaningful equation with n physical variables, then we can rewrite that equation as P, which is equal to n minus k, and we'll get to what k is, as P dimensionless parameters. And we traditionally write those parameters as capital Pi 1, capital Pi 2, all the way to capital Pi P. Hence the Pi theorem part, where k is the number of physical dimensions. Physical dimensions involved. All right, so let's go through and let's use Bernoulli's as an example of how all of this works. So Bernoulli's, let's write it out if we remember. Bernoulli says pressure divided by rho is equal to, plus v squared over 2 plus gz is equal to a constant, right? So if we were to look at this equation, we would say that it has 1, 2, 3, 4, 5 physical variables, okay? So it has pressure, we're going to write these over here on the left-hand side, density, velocity, gravity, and height as its physical variables, variables that are related to physical things that are physically realizable, right? A constant, for example, is not physically realizable. Then we can rewrite that equation as P is equal to n minus k dimensionless parameters, where k is the number of physical dimensions involved. So we have 5 physical variables, that's n. So what is k? K is the number of physical dimensions, and if we look at this, we have, if we break this down, we have g, which is meters per second squared. So we have time and distance, so we have length and time. Let's write those down. Z is length, so we have length already. V is distance per time, length per time, so we have length and time already. Density is mass per length cubed, so let's add mass here. And pressure is newtons per pascals. It's pascals, which is newtons per meter squared, which is a kilogram meter per second per meter squared, which gives us mass, length, and time, which we already have. So we have 3 physical dimensions. We have 5 physical variables, which means we should be able to rewrite this equation in terms of a 2 dimensionless parameters, pi 1 and pi 2. Okay? And we'll talk about how we're going to do that later and do some examples with that. But the important thing to remember here is it says if we have a physically meaningful equation, the mind-blowingly powerful part of this is we do not need to know the original equation. All right? So imagine now, for example, let's go back to Bernoulli's for a second here. With Bernoulli's, let's say we have a problem where we're like, oh, shoot, dang. Oh, what happened? Sorry, guys. We have a problem that's like, shoot, dang. What? Well, we know that when we vary the pressure, stuff happens. We know that the density of the fluid is important. We know that the velocity of the fluid is important. We know that the height of the fluid is important, and probably gravity, because if we do this on the moon, it's going to be different, right? So we have 5 parameters like this. We know that there are we have 5 physical variables. We know that there are 3 fundamental physical units. So that means we can come up with 2 pi groups. And that's all we need to know. We just need to be able to guess that there are 5 physically important variables, right? And so if we have some unknown function f of what we'll say q1, q2, q3, to qn, we have some function. We don't have to know that function. Then we can write that we know that f, we can write another function of pi 1, pi 2, pi 3, all the way to pi p is equal to 0, where p is equal to n minus k. Now, something important, a caveat. If we don't know this function, we've got to be honest with ourselves. We don't know this function either. We just know that it exists. Okay? And now you're like, wow, you've been talking this up for, I don't know, like 10 minutes now. And I'm like, yeah, I have been talking it up. Because even if we don't know this equation, the fact that we know that these parameters exist, these pi groups exist, allows us to fairly easily get this function through experimental work, which allows us to do a tremendous lot of really good experimental work that we couldn't do otherwise. And we'll talk about that now using the example of a ball in uniform flow. So with a ball in uniform flow, let's look at this. What are the parameters that are important here? What are the physical variables that are important? Well, we have air. Let's draw it in red. We have air where the viscosity is mu, the density is rho. So we know that we're going to guess through some experience that the density and the viscosity are both important parameters. This air is moving with a velocity v. Okay, we're talking about a physical property of a fluid that we think is going to be important, so we better write it down. Velocity v towards a ball with diameter d. That's a physical physical variable, sorry. And we're trying to figure out what the drag force is on it. That's a physical variable. So we have 5, n is equal to 5 physical variables here. How many experiments do we need to do to fully characterize this phenomenon? All right. So let's assume, just for the sake of simplicity here, that we're not going to independently address mu and rho, because those are coupled usually by the material, although you can vary them through temperature and pressure somewhat. Let's assume that we'll have to use we can look at just 10 different materials here for our experiments. We're measuring F. That's what we're measuring in our experiment. So we're just going to measure that. And we're going to vary the velocity, let's just say just 10 times. Okay? And we're going to vary the diameter of our ball 10 times. Well, that gives us 10 times 10 times 10 experiments, which means we're going to have to do 1,000 experiments. And let's be clear, we have barely scratched the surface here. We don't know how the force is going to behave with velocity. If it behaves something like this, and we only do experiments here, 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 and here, we might completely miss this behavior, right? 10 experiments is not nearly enough to fully characterize the system, and yet we have 1,000 experiments that we have to do. And trust me, you guys don't know this joke yet. I'm going to use this multiple times. You don't know this, but grad students do most of the science in universities, right? Because as part of their training, it's an apprenticeship. So we have them do the science to learn it, and then when they graduate, they've proven themselves. But as a result, they end up doing most of the work, just like most apprenticeships where they used to have stone carvers apprenticeships. Well, the apprentices would do most of the work, and the stone carver would walk around being like, oh, that's great, that's bad, whatever. So anyway, we don't have enough graduate students to do 1,000 experiments, let alone the tens or hundreds of thousands of experiments we would need to do in order to fully characterize this phenomenon. But enter the Buckingham Pi Theorem. So Buckingham Pi Theorem tells us that we will have n minus k pi groups that we know will enter our function, right? And so we have 5 here. We have n is equal to 5. And again, we have, if we write these out, we would know that our force, actually we've done most of these already, right? Viscosity, this density we know has a mass. That means we have a mass in our system. We have a length and time from our velocity. We have mass, length, time in our force. We have mass, length, time in our viscosity. And we only have length in our distance. And if we're being honest with ourselves, there's only a handful more of physical dimensions. There's, if we wanted to talk about them, there's temperature, there's charge, and I can't really think of much else. There might be something else, but I can't think of it right now. So you're rarely going to have anything more than 3. You might have 4 with temperature and fluids. And if you're really doing some fun stuff, you'll have all 5. But here we have 3, right? So we have 5 minus 3 is going to give us 2 pi groups, okay? And now I'm going to give away the climax of this story here. I'm going to tell you what those pi groups are. Pi 1 is going to be equal to our force, because remember that's one of our physical variables, divided by, and now all the rest of the units that are included in here all the rest of the variables that are included in here are going to have to cancel out the units on our force. And so we're going to have density, velocity squared times our diameter squared. And our pi 2, by the way, we'll get to it. Pi 2 is going to be equal to, if we solve for it, rho v d over mu. Now this is our Reynolds number, also known as Reynolds number. And this is our drag coefficient, right? And what Buckingham Pi Theorem tells us is that some function exists of our drag coefficient and our Reynolds number that completely characterizes our system, okay? And any function like this we can rewrite. We can rewrite this as f over rho v squared d squared is equal to some unknown function g. Remember, f is unknown. We don't know f. We can pretend like we rewrote this into some unknown function of rho v d over mu. So what we've learned is that our drag coefficient can be thought of as a function of our Reynolds number. And how this becomes super powerful is now we want to do, let's say we do 1,000 experiments, but now we only have one independent variable and one dependent variable. Before, if we scroll up, we had one dependent variable and either 3 or 4, depending on how you counted it, independent variables. So we had a tremendous number of experiments in order to cover our area. Here we only have one independent variable, this Reynolds number, which is a combination of other ones, but as long as that combination is the same, then we would expect this ratio to be equal to the same number. And so let's talk about what that means. That means that for a given ratio of rho v d over mu, and let's say we double our velocity, as long as we cut in half our diameter, our Reynolds number is going to stay the same, and we'd expect this unknown function g to give us the same number that this drag coefficient is equal to. So we can change around the density, the viscosity, the velocity, and the diameter. As long as we have the same Reynolds number, this drag coefficient will equal the same number, okay? And that's super useful. That's super useful because as an experimentalist, then what we can do is we can do one experiment like 100 times, and we can take our CD, this is our drag coefficient, and make it a function of our Reynolds number, and we can write out this function, and this is actually what it kind of looks like. Oh no, drag crisis. We'll talk about the drag crisis later. It's probably one of the more fun things in all of fluid mechanics. This drag coefficient Reynolds number relationship works for, I won't say all, because if you get towards compressibility effects, then this doesn't work. But then you're missing out on some stuff, but we'll talk about that in a little bit. So it doesn't work for everything, but as long as you're within a certain range of Reynolds numbers, you'll be able to calculate your drag coefficient for your object. And that, again, is incredibly useful because we went from having 1,000 experiments to do a pretty shitty job to 100 experiments and actually fleshing out our curve quite well, right? And then if we wanted to flesh it out more, we could do more in areas like, let's figure out what's going on in this drag crisis area. So the second formulation of Buckingham Pi Theorem is really the most useful. We say that pi 1 is equal to some function g of pi 2 through pi p. And this is the one we'll use in this class. And we'll often ask you to give pi 1 as a function of the other pi groups. This is all we're talking about. That's all we're talking about here, right? We're just asking you to restate Buckingham Pi Theorem. All right, so let's give you a few hot takes on Buckingham Pi Theorem, and then we'll do the next video. We'll talk about how we find these pi groups. So, 1, Buckingham Pi Theorem is awesome because it can greatly simplify the modeling of physical phenomenon. All right. So drag on our ball went from 5 dimensions to 2 dimensions. That's incredible. That makes it possible for us to completely map a relationship experimentally, which is incredibly useful. 2, let's say we don't know g of pi. Oh, I said h. It's pi. Pi 1, or sorry, pi 2, pi 3, all the way to pi p. Oh man. Pi p. Let's say we don't know this function g, and we want to predict the behavior of a prototype based on a model experiment. All right. We know that if pi 1 of our model is equal to pi 1 of our prototype, and pi 2 of our model is equal to pi 2 of our prototype, all the way to pi p of our model is equal to pi pp of our prototype. If we know all those are true, then this function, right? We don't know this function, but it is a function. And what makes a function is if you plug in the same numbers, you're going to get the same value, right? So if we plug in all of these into our g, we're going to get some value for our pi 1. And that's got to be equal to these because there's the same number. We're plugging the same number in here, and that means that our pi 1 for our prototype has to be equal to the same thing. So we can calculate pi 1 for our model and know that that's what our pi 1 for our prototype has to be, even though we can't do the experiment for our prototype. So for example, with our ball and air experiment, let's say we have a model where we have this ball and we have a prototype where we have this ball, which, okay, this isn't useful. Let's do some scaling here. Let's say this is a person, like a basketball, and this is the same person, and this is some gigantic ball, right? Let's say this is our model, this is our prototype. We can do an experiment on this, right? This is experimentally achievable, but the prototype is not. So we can go up here. We can say, listen, we know that f divided by rho v squared d squared is equal to some function of rho v d over mu. We can measure Reynolds number, and as long as we match the Reynolds number for eventually what our prototype is going to be used for with our model, then we know that f over rho v squared d squared for the prototype has to equal f over rho v squared d squared for the model. So we can measure this for the model and know that it's equal to the prototype. So then we can say that f model over rho model v squared d squared model has to equal f prototype over rho prototype v prototype squared d prototype squared. And we might not know the f on our prototype, but we can guess the density, velocity, and diameter of our prototype. So that means we can eventually calculate the the force on our prototype, even though experimentally we could never get a wind tunnel maybe big enough to actually fit this ball in it, right? So this, if matching pi 2 through pi p, and then using those matching those is called similarity. So once we have similarity, then we know that pi 1 is equal to pi 1, and we can actually solve for some interesting things in our problem, right? And that's basically, by the way, what we're doing here when we do a bunch of experiments and plot our Reynolds number. We're saying, all right, here's the Reynolds number for our model in a wind tunnel. And if we are at the same Reynolds number for our prototype, then we know what our drag coefficient has to be. We might do an experiment on a basketball-sized sphere in our wind tunnel, but we can then use that to guess the drag coefficient of, say, a baseball or a golf ball, or who knows? I don't even know what a huge giant. Well, remember there's one time when they landed a rover on Mars by putting a whole bunch of like a spherical balloon around it so that would bounce when it hit the ground. That kind of thing, right? We could guess the drag force on that thing, even though the atmospheric properties are different. Excellent. All right, so that's a lot for right now. Next time when we get to a video, we're going to talk about how to find these pi groups, and then we will we'll find them, and then we'll talk about what happens if we make some different decisions in the process of finding them, and we'll talk about the meaning of some of these dimensionless groups. And then after that, we'll do some videos where we practice all of this. All right, great.